Last time we introduced how to do automatic sound memory management with the mark and sweep algorithm. And recall that the mark and sweep algorithm, if we were to talk about its performance, there are two dimensions. There's its time, where we can talk about how expensive Malloc is. And Malloc is O log n, because it searches a tree. Free doesn't cost anything because we reassemble the free list when we are doing the sweep phase. And then the garbage collection algorithm itself takes O live, because we have to walk across of all live objects and mark them, plus O memory. And of course, memory is larger than live, so in just terms of big O notation, this is just O memory, because we have to walk across all of memory and unmark everything, and reconstruct the free list and actually retrieve the space. Now in terms of space, we can talk about the overhead. And essentially the overhead is just the mark bits. We don't actually have to pay for the free list because we can store the free list inside of the free memory locations. Now how many mark bits are there? Essentially there's O log memory, because potentially every spot in memory could be used. Now in terms of the latency, I guess this is not really a space thing. This is really another time thing. Let's do this. This is something that's cool about not using paper. Look at that. Amazing. Latency. We can use incremental collection. All right. Now, mark and sweep basically represents one side of the spectrum of how we might design an automatic memory management algorithm, and it is really optimized in terms of space. It uses very small amount of space overhead, but it pays for that by having an expensive Malloc and an expensive garbage collection. As I alluded to before, it might feel like this Malloc is actually that expensive because this is sort of the norm. If you use a garbage collection strategy, if you use a memory manager like the manual memory management that you would get in C, you're going to pay this cost for Malloc. So mark and sweep doesn't seem particularly slow, but from the perspective of this next algorithm that we'll talk about, it's actually quite slow. So this new algorithm, it's called stop and copy. And let's talk about its performance. So its Malloc is going to cost O1. So that's going to be really fast. Like before, its free is going to be free. Its garbage collector is also going to be fast because it's going to be O live, meaning that it's going to ignore memory that is dead. However, and here's the downsides, its latency is going to be high. There's going to be no incremental mode. And its space is going to be even worse. Its space overhead is going to be times 2. It's going to use twice as much memory as mark and sweep would, right? Well, actually as the normal program would. So, stop and copy is the other end of the spectrum. Whereas mark and sweep is optimized for space, stop and copy is optimized for time. Let's think about how it can work, and then we'll walk through the algorithm. And what I'd like to do is I'd like to start from what our goal is, our goal being the speed, and then we'll derive an algorithm, and we'll see why that algorithm has this space overhead. So our goal is O1 Malloc and O live GC. Okay, so what does this mean? Well, why does mark and sweep have a malloc that's expensive? So the mark and sweep malloc searches a tree. It searches a tree, and that means that we have this tree that represents all of the possible locations in memory that are free. Okay? And what we need to do is we need to search down this and find the one that we care about. And that's how you get the log n. Because the size of this tree is basically the size of memory, essentially. And we need to search inside of that tree to find the thing that we care about. Okay, well, with this new algorithm, stop and copy, it must be O1. So given that it must be O1, it must be obvious where to malloc. Obvious meaning that we have to be able to do it without resort to a data structure. Now let's elaborate on why exactly we need a tree for malloc. So imagine that this is memory, right here. And I'm going to imagine that it is allocated with mark and sweep. And initially, the entire all of memory is free. And then maybe we get a request for allocating A, and it's this big. Then we get a request to allocate B, it's this big. Then we get a request to allocate C, it's that big. D, it's this big. E, it's this big. And then at this point, a request comes in to allocate, let's say, F. But F would be too big. So in that case, we do garbage collection. So we go through and we mark. And let's just suppose that when we mark A, we mark C, and we mark D. Okay? So we mark those three things. Then after we do garbage collection, what happens is that A is still here, C is still here, D is still here, but then this region and this region are now empty. So that means that our free list, really it's a free tree, but I'm going to draw it as a free list. Our free list says this is free, and then that says this is free. Okay? Now what we need to do when we get a malloc request, like for F, we have to search through this set of values and find the one that's the appropriate size. Obviously you could do that in a purely linear fashion by seeing if this is big enough and if it's not, seeing if that's big enough. But since this is just a data, we're just searching a collection, that's why we know that we can store it as a tree, and then we can do it faster with O log n. All right. However, stop and copy has to only work with O1, meaning that it can't search. It has to always know exactly what is going to be, where the next spot is going to be. And so because it has to know exactly what the next spot is going to be, that means that its malloc basically can only be implemented like this. So malloc is going to take a size, okay? And what it's going to do is it's going to say if the free region, we'll call that the free pointer, plus the size is less than the total size, then what we can do is we can set the free pointer to be plus equal the size, and then we can return the free pointer minus the size. We're basically returning what the free pointer used to be. And then otherwise, at that point we need to do a garbage collection, and then we need to try to malloc again. Okay? So this right here is the implementation of Malloc inside of stop and copy. And what it does is it just uses two variables. It uses a free pointer, and it uses the total size. All right. Now, let's think about how Malloc would work, how that same sequence of operations would work. We would allocate A, we would allocate B, allocate C, allocate D, allocate E, and then a request for F comes in, but it's too big. Then we go and we do garbage collection, and let's just assume that it works the same way as mark and sweep. And we mark these things, okay? And then after garbage collection, we would end up with this. Okay, now we have to say what the free pointer is going to point to. See, it used to be that the free pointer pointed to that spot right there. And this value right here, that's total size. Okay, so afterwards, this is still total size. But the question is, what should the free pointer point to? If it points to right here, then that means that we could give up the space for C. So we can't point it there. We have to point it right here. And because we have to point it right there, that means that we reclaimed this space right here that used to be part of E. But this space is permanently gone and we can never use it. And the reason we can never, we can never use it because we'll never know if that region is needed or not. And so that's obviously problematic. So what we're going to do is we're going to say, we're going to fix Malloc as being O1. We're going to take that implementation that I showed and guarantee that Malloc is always that. But then we have to go work around and solve all the other problems to make sure it still works out. All right. So now, that was step one, discovering the Malloc that we need. So now let's discover why GC is O live. How can we make sure that when we run out of memory, we don't have to look at anything that is not a reachable object? Because that's really what OLive means. OLive means we look at the reachable objects and we ignore the objects that are not reachable. We totally ignore them. So let's use a little analogy. So my kids have a playroom. And what happens is they come into the playroom and they play with some toys. So maybe they'll play with a doll. I don't know, that's a really weird looking doll. Okay, so they play with a doll, then they read some books. This is going to be a spiral-bound book, maybe. Okay, then they may do some painting. Okay, and then maybe they'll play on the piano. So how do we do? How do we draw a piano? Okay, so they play on the piano. Now this is their playroom. Now I tell them, you have to go clean up. So then one child, this is my oldest boy, the way that he cleans up is he goes into the room and he makes a pile in the middle of the room of all the stuff that they don't want, that they don't care about. And he has this big pile of trash in the middle of the floor. Because, every time they play, there's little scraps of paper, there's all sorts of stuff. So they make a pile of the stuff that they don't want. And then while they're making that pile, they also find the stuff that they care about and they go put it where it belongs. And then at the end, the room that used to be really, really dirty now has a nice little pile in the middle, and they go in and they sweep that up into a bag, they take that and they go throw it out, and then now the room is clean. So that is mark and sweep. They first have to identify the stuff that they care about, and they have to identify the garbage and go through and clean it up. But I have another child. This is my second youngest girl. I have 5 kids. This is my second youngest girl. And she is an inventor, okay? And so she loves trying to discover some sneaky way of doing something. So this is what she does. She says, "Daddy, could I have another playroom?" I say, "Oh, yeah, sure, you can have another playroom." So then she has another playroom. And she says, "I want this playroom to be exactly the same size as my old playroom." I'm like, "Okay, sure." And then what she does is she says, she looks in this room, and she just looks at the stuff that she actually wants to play with again. Because, there's trash on the ground, there's toys that are broken, there's stuff that she doesn't want anymore. And so what she does is she takes the stuff that she wants to play with, and she moves it into her new room. And she knows that this room, it's the same size as that room. So maybe she actually likes everything and she'll move it all over. But maybe she doesn't. Then what happens is after she moves everything into the new room, she has only looked at the live stuff, the stuff that she cares about. And she looks at that other room and she says, if I left it in there, I must not care about it. So then she takes a match, lights it, throws it into the room, it goes up in flames, and everything inside of there is gone, and she never even had to look at any of the dead stuff. This is an analogy for how stop and copy works. How stop and copy is going to work is it's going to have the region of memory that you're using. And then it's going to have another region of memory that's exactly the same size. That's why the space is 2x. Because we need your normal amount of space plus 1 to just be dormant. Okay? And then what we're going to do is we're going to go through the live objects and copy them over. And once we copy them over, we'll know that whatever was in the old space isn't needed anymore, so then we'll just forget about it. And that space will become the region that we'll copy to next time. All right, so let's look at an example of doing this. All right. Suppose that we had allocation like this. A got allocated, actually let me draw it as a line. So here is memory. I wonder if it's possible to make it so that this page has a... There are these things called templates in this thing where it can be grid. I could make it so that they're gridded, and I could make sure that they're the right size, but let's not care about that. Okay, so we get an allocation request for A, we get an allocation request for B, we get one for C, D, E, and then we're going to do collection. And let's imagine that this whole thing right here goes from address 0 to address, how many things are there? I don't know. Let's say that A goes from 0 to 20, B goes from 20 to 30, C goes from 30 to 40, D goes from 40 to 50, and E goes to 65, and then this whole region right here is, let's just say that it's 70 big. Okay? Now, that's a 70 by the way. Actually, let's make it an 80, just because. Okay? All right, so now, this is what we're going to call the from space. The from region. Then what we're going to do is we're going to have another region that's exactly the same size, but of course is stored somewhere else in memory. And this is going to be called the to space. So it's going to go, let's say it's going to start at address 100, and it's going to go up to 180. Okay? Now, let's imagine that there is a pointer that comes from outside, let's say it's variable x, and x is equal to 0, meaning that it's a pointer that is pointing at A. And inside of A, there is a 30 in there. Okay? And that 30 is, of course, a pointer to C. And inside of C, there is a 40, which is a pointer to D. All right? So this shows us the linear view of memory, and this shows us the and then this shows us the heap structure of memory. Notice that there's no pointer to B and there's no pointer to E. Now here's how stop and copy is going to work. the first thing that stop and copy is going to do is it's going to say, aha, x is in our root set. So what I'm going to do is I'm going to change x so that x now points to 100. And then what I'm going to do is I'm going to copy from 0 to 20 over to here. So now it says A, and there's a pointer to 30. Okay, so all I did was I updated x to be 100, and then I moved this down here. And what I'm going to do is I'm going to have my free pointer be updated. What I did is I set x equal to the free pointer, then I copied from what x used to be to its size over into here. So basically I malloced the size of A, and then I copied it over. All right. What I'm also going to do is I'm going to have a pointer that's called toCopy, because I need to copy this thing. Actually, let's not call it toCopy. Let's call it toScan. Let's call it the scan pointer. So then what I'm going to do is I'm going to look at the scan pointer and say, here's an object that I haven't scanned yet. Let's look inside of it. Aha, there's a 30 there. What I'm going to do is I am going to change that 30 to 120, because that's what the free pointer is right now. And then I'm going to copy this memory over. So I copy object C. Okay, and so it starts at 120. And notice that I update this so it's no longer pointing there anymore. Now it's pointing over to here. And C has a 40, and that 40 is pointing up to here. And this is 120. Then what I'm going to do is I'm going to update the free pointer so it now points over to that spot. And I'm going to update the scan pointer so the scan pointer now points over to here. Okay? So what I've done is I've copied A over, then I looked at what A pointed to, and then I copied C over, but I haven't looked at what it points to yet. Now I'm going to look at the next thing that the scan pointer points to, and I see, aha, that's D. So what I'm going to do, make sure I got this right, is I'm going to set this 40 equal to 140, which is what the free pointer is currently at. Okay. So because I did that, now it doesn't point to 40 anymore, it points to 140. And then I copy D over, and D goes up. Hold on, I made a mistake. It's not 140. It would be 130, because A is 20 big and C is only 10 big. So it would be 130, and this is 130. Okay, now I've copied D over, and D doesn't have any pointers inside of it, and so it goes up to 140. Okay, the next thing that I do is I update the free pointer, because I just allocated, so that now the free pointer, it points to 140. And then I update the scan pointer, so it points to D. Okay. Then I go and I look at the scan pointer, and I see if D points at anything, and it doesn't. So that means I can now change the scan pointer and I point at the object that's after D, which is the same thing as the free pointer, and then I know that I'm done. I've copied everything. Notice I never looked at B, and I never looked at E. Now my free pointer is pointing at 140, and I've got all this empty space. I now change in my head, I now switch and say this is now the from space, this is now the to space, and then I continue allocating. My program, it used to point to 0, but now it points to 100. So my program keeps running. This algorithm is called the Cheney queue algorithm. Or maybe we should say it is the Cheney queue implementation of stop and copy. All right. Now, there's one more little thing that I need to describe about how stop and copy works. And that is that there's a slight problem with what I've described with cycles. Imagine that we have object A, and it's stored at address 0. And then it is pointing to object B, which is stored at location 20. Actually, let me use this. I don't really like what I did there. Okay, so we have X, and X is pointing to address 0, and that is A. And A is pointing to address 20, and that is B. Now let's imagine that B is pointing at object A, at address 0. Now what happens when we copy? What happens when we copy is going to be this. We're going to say that X is now going to point to address 120, which has an A there. And at address 0, there's still an A. Like A is still there. And then it is pointing to B at address 20. And this is also pointing there. And this is pointing up there. Okay, so let me just put a little box around this. So this is state 1. This is state 2. Let me move all this over. Okay. What happens next? What happens next is that now what we do is we scan this A. So then we have it so that, so we scan that A. So we have X is pointing to 120, which is pointing to A, which is A. And then it is now pointing to, sorry, this is annoying. We don't want that to be 120, we want that to be 100. Sorry, that was stupid. So it's pointing at 100, so that's at 100. Now A is now going to point to 120, which is a copy of B. But the 20B is still there, okay? And the 0A is still there too. And this one is pointing to there, and this one is also pointing there. Okay? So that's the next step. So this one is from scan X. This is from scan A. Now what's going to happen is that we're going to scan B. And if we do what I've said so far, when we scan B, what's going to happen is that X is going to point to 100, A. A is going to point to 120B. All right. And then B is going to point to 200A. And 200A, it actually still points down here to 20. So it's going to point way over here. Whoops, sorry. These objects still exist. This 0A, which is pointing to 20B, which is pointing to 0, and this thing is going to point to that. And what's going to happen is that we're just going to keep making copies of A and B over and over and over again. Okay, so this obviously is wrong. Here's what we need to do. After we copy, we update the old object with a forwarding address. So here's the way that it's going to look. X is going to point to 0A. A is going to point to 20B. B is going to point back to 0A. That's going to be the first state. The next state, we are going to copy A. All right? So when we copy A, at 100, we're going to put our new A, and it is going to point to the old 20B. All right? And the 20B, it is going to point to 0. And X is going to point to A. But inside of here, it's not going to say A, it's going to say moved and have a pointer over to there. All right? And moved is going to be a special thing that we can identify. In terms of like how your low-level implementation works, this is basically a new kind of object, like a new tag. You have conses, you have ifs, you have numbers, you have bools. One of them is going to be called moved. We call it forwarding pointer. Okay, so then what's going to happen is that we're going to scan B. And so when we scan B, we're going to say that X is going to point to 100A, and then A is going to point to 120B. 120B, it is going to point to 0 moved, which is going to point to that. And there's going to be another moved that points to there. But no one's pointing to this. Then we're going to scan B. And here's the thing that's special. When we scan B, if it points to something that's already been moved, we just update the pointer. So after we scan B, X is going to point to 100A, which is going to point to 120B, which is going to point back to 100A. And then there's still a 0 moved, which points to 100, and a 20 moved that points to 120. But at this point, the scan pointer equals the free pointer, and then we're done. And so then we burn. And when we burn, we're left with only X goes to 100A, which points to 120B, which points back to 100. These forwarding pointers ensure that we don't get stuck in an infinite cycle when we're copying. And the key thing is that when we copy, we create a forwarding pointer over on top of the other space. So that actually has kind of a weird consequence, which is we have to ask the question, how big is a forwarding pointer? Well, it has to have a tag, and it has to have a pointer. So tags are always the same size. And all our objects always have those. But a pointer is word-sized, meaning it's 64 bits on a modern machine. So that means any object must be able to be changed into a forwarding pointer. Because no matter what it is, if it's stored in memory somewhere, it might someday be moved. So we need to make sure it can be turned into a forwarding pointer. Therefore, all objects must be at least word-sized. So that means that anything that's not word-sized, we have to expand it to be bigger. It's kind of annoying because, like your bools, for instance, your bools are probably going to be a tag plus, like, they only need a single bit to say whether they're true or false. So this is going to make them bigger. But, you know, so it is. So we now have seen mark and sweep, which is a collector that's optimized for space. Stop and copy, which is a collector that's optimized for time. And notice that calling it a garbage collector isn't really a good name because it doesn't actually collect any garbage. It only collects good stuff and then can totally ignore the garbage. And that's why it is so efficient. All right, next time we'll talk about another memory management strategy.